All right, so last time we covered, or we started chapter 20 with carboxylic acids, looked at the melting points, acidity, and so forth. And today let's get further into that and look at this important topic here of carboxylic acid salts. Okay. So remember last time we looked at the functional group of carboxylic acids, okay? And we found that this hydrogen here was acidic. Well, today what we're going to do is go ahead and react it with a base, something like potassium hydroxide. Okay? So remember, when you see KOH, for example, you can write it as K plus and OH minus. So the OH minus is the basic part. Where will the OH minus attach over here?
No, the hydrogen. It's inside the A.
Right. Base attacks the acid. Okay. So let's go ahead and show that here. So if I take that acidic hydrogen, then we get this set up here. Okay, and this thing here is our carboxylic acid salt. Okay, so remember the definition of salt is when you have a metal cation and an anion together. Okay, so we've seen salts before in general chemistry, like potassium chloride and sodium chloride and other such things. Okay. So these are carboxylic acid salts. Let's look at a real acid here, acetic acid. And let's react it with KOH. Okay, so that the resulting salt forms like that there. Okay. We want to look at two things about these salts. One thing is how to name them. Then the second thing is their properties, okay? So let's look first of all at how to name these, okay? When you have a regular salt like this here, you name the metal first, so that's potassium, and then you name the anion second, chloride, okay? Why don't you shut that door? So we'll do the same thing down here. We'll name the metal first potassium. Okay. Then the acetic acid has changed. It's become O minus, and so the ending will change to ATE. So we get potassium acetate. Okay, that's how we name these metal salts, these carboxylic acid salts. how would you name that salt there? Sodium. That comes from benzoic acid. So we get sodium benzoate. So we drop the ic acid and add 8, okay? One more, how would you name something like that? Lithium. And how many carbons? 2, 4, 6. Six is hexanoic acid. So drop the ic acid and add 8. So you get lithium hexanoate. Okay. Any questions on how to name carboxylic acid salts? Okay. So that's the first thing we want to look at these things for. The second thing to talk about is their properties. Okay. Come back and look at this salt, potassium chloride. What's one of the main properties of potassium chloride? Anybody, any ideas? When you put it into water, what happens? It dissolves. It dissolves nicely, doesn't it? And it dissolves completely, so that if you put an electric current, it would pass electric current, so we call that strong electrolytes. Okay? So, same thing here. These carboxylic acid salts are water soluble. Okay? So that's a nice important property about these things. Okay? So let's take a look at something here. Okay. Let's, for example, look at benzoic acid. Okay. You might remember from 241 that if you take benzoic acid and put it into water, it doesn't dissolve. Okay. It's water insoluble. Okay. What you would see is a bunch of white flakes floating on top of the water. But if you added, for example, some sodium hydroxide, you would convert the acid to its salt. Or sodium benzoate, and this sodium benzoate would be water soluble. So if you shook the flask with some sodium hydroxide in there, you would soon see those white flakes dissolving into water very nicely. Okay, so it's a nice little demonstration to do. Well, how could you get the carboxylic acid back? What would you have to add to that? I need to get a proton back. How could I give it a proton? Give it, added an acid. Something like HCl. Okay? So the oxygen would take that hydrogen and you would reform that benzoic acid, which would be water insoluble. Okay, so you would see the white flakes again, or stuff floating down to the bottom of the flask, and so on. Okay, then you could take this and react it with some more sodium hydroxide, and it would dissolve, then add some more HCl, so you could keep doing this thing over and over. So it's a nice little demonstration, you know, if you ever visit high school students or whatever, it's a nice little demonstration of acid-base chemistry. And they sit there and say, wow, okay, it's disappearing, oh, and it's back, okay? Kind of a neat little trick to show, to demonstrate acid-base properties. Okay. Any questions on that? Okay. Let's look at one other thing here about these acid salts. Let's suppose we had this acid salt. Okay, you don't have to draw it exactly, just draw a bunch of carbon atoms there to get the point across. Okay? When you have something like this, you can see you have a long carbon tail. See that? And that long carbon tail we generally call a fatty tail. Okay? So when something has a bunch of carbon, a long string of carbons, it makes it real fatty. Okay? Kind of reminds you of what? Fatty acids. What are fatty acids? With the acid group, but long carbon chains. Okay? So you have a fatty tail here. And since this has a bunch of carbon atoms, it's nonpolar. So that part there would be water insoluble. But this part over here would be water soluble, because that's the salt portion. Okay? So water can tackle that part. But this stuff here, it wouldn't. So you got half of it dissolving into water and half of it just sticking out. See that? Well, what would happen if I had a bunch of these and I put them into water? What would happen? What would happen is you would find them all bunching together like this. Let me just use a little diagram. Okay, so you get the point. So you would get the fatty tails bunching together on the inside, and the polar tails on the outside, where on the outside you have water, so that's the attraction with polar, and on the inside you have nonpolar, so those like to mix together. Okay. And so you get this kind of structure forming. Okay. Taking notes back there? Got a lot of paper. And this structure here is what's called a micelle. Have you ever heard of a micelle? Biology? Have you heard of that yet? Okay. So that kind of thing there forms, and this is how soap works. okay? The soap that you buy and it suds up, what happens is, when you wash your hands, the dirt is usually fatty of some type, and so that mixes with the fatty tails, and then the polar tails mix with the water, so it takes it down the sink. Okay? So that's the mechanism of how soap works. Okay? But you see micelles also in your body. Okay? Have you ever heard of what are called phospholipids? Okay, so I'm sure you've heard of that in Bio 101 or whatever. Okay? Where do you find phospholipids? Where? Layers of your skin and cells and so on. Okay? Okay? So in a cell, okay, what you have is the outside wall of it usually being a phospholipid, and when you look in your biology books, you see the squiggly lines, don't you? Okay? But what do you see on one side of the squiggly line? Okay? You see polar tails, don't you? Okay? So on one side of it, you might see polar or whatnot. Okay? So these phospholipids kind of go with the same kind of principle. We got a fatty part that mixes with your fatty parts of your tissues and so on. Then you got the polar part, which mixes with water, so that helps to allow, remember, maneuvering of different atoms across the cell wall and so on. Okay? So I'm not a biologist, so my knowledge stops about there, okay? But you get the idea. Okay? So, has anybody taken cell biology yet? Kafuri or Stevenson? Okay. So you'll get into that a lot as well. Okay, so that's carboxylic acid salts. Okay? All right, well, let's move on to our next topic. We're going to get into the chemistry of the chapter. Okay? And what we want to look at first is how to make carboxylic acids. Okay? If you look on your outline, there's a few ways to make them. Okay? The first and primary way is we start with a primary alcohol and we react it with this mixture here. Okay. So this thing here, Na2Cr2O7, this is what's called sodium dichromate. Okay, and of course, this here, you know, is sulfuric acid. Okay, and sodium dichromate, anytime you see this chromium atom in here, this is a very strong oxidizer. You remember that, okay? Not only is sodium dichromate a strong oxidizer, but also sulfuric acid. If you pour sulfuric acid on your hand, you'll see it oxidizing your hand very quickly, turning yellow, and then some other nice colors. So let's look at this reaction. So if I have a primary alcohol, okay, such as ethanol, and react it with this mixture here. Okay. So what it will do is convert the carbon with the OH to the acid group. And so that would be one way to form acetic acid. Okay. Okay, so you can see it oxidized it. I added oxygen and I added a double bond. So it's a very strong oxidizing reagent that we've used. Okay? But it has to be a primary alcohol. Okay? Another example of this might be if you take benzyl alcohol, and react with our mixture. Okay, so it's a primary alcohol. So this portion here would then become the acid group to give us benzoic acid. So here's a new way to form benzoic acid by oxidizing benzyl alcohol. Okay, so this is the first main reaction to have on your note cards for this chapter. Okay, any questions on this reaction? Okay. All right. So it's very similar to the PCC reaction. Remember that? Mm-hmm. That converted what? A secondary alcohol to a carbonyl. Okay, or a primary one to the aldehyde. Remember that? So it wasn't as strong as this, okay, but the same principle. Okay, guarantee you'll see PCC later on today. Okay, let's look at a second reaction. This one is by way of review. Okay, this is where we have an alkylated benzene ring. Okay, so we have some alkyl group on there, like a CH3 with toluene. Okay, remember this reaction where we used KMNO4? Remember that one? What happened in that reaction? It converted the alkyl group to the acid group to give you benzoic acid. So remember, again, it didn't matter if it was one carbon or a bunch of them. It would clip off a string of carbon atoms to the acid group. Okay. So that was another way to make benzoic acid. Okay. Let's look at a third reaction. Here, this is the use of CO2 or carbon dioxide. Okay. So what we do in this reaction is start with a grignard. Okay? Remember what a grignard was? Something else you'll probably see later today. Okay. So let's just do a review of that since we're on that topic. Remember how to make a grignard. You start with an alkyl bromide, like that, and we react with magnesium, okay? And remember, the magnesium inserts itself between the Br and the carbon. Okay. What was the main property of grignards? What do you do if you ever see this? Take off this MGBR and put a lone pair on that carbon where it's attached. Okay? So very good. So this thing, for all practical purposes, acts like that. Okay? So in other words, it's going to act as a nice nucleophile. Okay? So in their aldehydes and ketones, remember that could go on and attack the carbonyl and convert it to an alcohol. But here, what we're going to do is take our grignard and react it with carbon dioxide. Okay? So there's the Lewis structure of carbon dioxide that maybe you're not familiar with. Okay? And if you look at the polarity of it, you would have a partial positive here and negatives on the oxygens. Okay? So where do you think this grignard is going to attack? Which atom? The carbon, because it has the positive. Okay? Then either one of these pi bonds can go to the oxygen. We'll just choose the right side there. And so now our carbon dioxide has added on. Okay? So that carboxylate ion was formerly CO2. Okay. Then lastly, we can react it with the hydronium ion. Okay? And what is the special property of the hydronium ion? I'm sorry?
It acts as a hydrogen, H+.
Okay, good. It acts as a hydrogen donor. All those hydrogens are acidic. So where do you think the oxygen will go? Grab one of the hydrogens. Very good. Okay. See a lot of good studying out there. So that ends up giving us the carboxylic acid. Okay, so kind of a neat little reaction, isn't it? Okay. Let's write a summary of it without all the mechanism part, okay? So what we just looked at was the mechanism. Let's look at it in summary fashion to kind of make it less messy here. Okay, so what we did, we started with the alkyl bromide. And we basically did what? 3 steps. Okay? First of all, reacted with magnesium, then carbon dioxide, and then protonated with H3O+. And that gave you the carboxylic acid. Any questions on the mechanism or the summary there? Make sure you're familiar with both. Okay. Let's go over one little thing here that you may or may not have spotted. Okay. If you look over on this side, how many carbons did we start with? 2. How many did we end up with? Okay, very good. So we have added an extra carbon, which came from the CO2. Okay, so make a note of that, where we extend the carbon chain by 1. Okay, so we end up with propanoic acid, not acetic acid. Okay, so that's one of the main properties that you want to take away from it. Okay. It's interesting, if you were to do this experiment in the lab, what you would do, it's very simple. After you mix these two to make your Grignard's in solution, then what you do is you take a canister of carbon dioxide and you bubble it into that solution. Just bubble the heck out of it, okay, for about half hour, okay? Then you get your carboxylate ion, and then you add acid, and then you're done, okay? So it's a nice little reaction to do. That's what they do with water to make your soda pop, is bubble the heck out of it with carbon dioxide. Okay. All right, so that's the reaction with CO2. Okay, so those are the main ways to make carboxylic acids. Let's now change directions of it and look at reactions of carboxylic acids. So what kind of reactions can these things undergo? Okay. We'll just look at one today and look at some others next time. Okay. Let's look at one that will be very familiar to one of today's reactions. That will be the use of lithium aluminum hydride. What did lithium aluminum hydride do to a ketone or an aldehyde? Reduce to a alcohol. Very good. Very good. Okay. What do you think it's going to do to the acid? The same thing. Reduce it to an alcohol. Okay. So let's take a look at an example. So what we do in this reaction is react sequentially with lithium aluminum hydride and then the hydronium ion. Okay? So you're right, strong reducing agent, so it's going to reduce the acid group. back to an alcohol. Okay, so kind of the exact opposite of where we started in class. Where we started in class using sodium dichromate and sulfuric acid that oxidized the primary alcohol to the acid. Well, now we just go reverse, where we reduce the acid back to the alcohol. Okay. Any questions on that reaction? Okay. So you can see as we learn organic chemistry, you can see how reactions you learned in one chapter of the book come back and they're right there again in another chapter, just on a different functional group. Okay? So all this kind of comes together after a while. Okay? Any questions on this reducing reaction? Okay? So next week when we come back, all the way a week from now, next Wednesday, okay, Easter break, we'll tackle the rest of chapter 1. When we turn this off, then we'll talk about the exam.